So in this clip, we're going to see an example related to the reduced density matrix that we have discussed so far, because it is quite still an abstract concept. And what we are going to consider is in the case where you would have spontaneous decay. Please note that this is some kind of semi-empirical model, because to fully treat spontaneous decay, you would need to quantize the field and consider its interaction with vacuum modes. So just to clarify, this is a heuristic description of spontaneous decay. Full theory will require field quantization and the interaction with the vacuum modes. Just that you know is heuristic. So what we have is, let's assume we have a two-level system whereby the excited state is E, the ground state is G. Then this system is initially in the excited state, decays to the ground state, and emits a photon. Of energy h bar omega. This is our assumption. Okay, so we're going to have a look. It takes a while here to decay somehow, and let's construct the state of the system. So first thing we can see, you have here a compound system of atom plus field, right? So this is a compound system of atom plus field, which is good because we can use the theory we have just learned, and we can then see how this is going to operate. All right. So we need to construct now this state for the compound system, and we can see the following. That we're going to have for the atom, we can have ground state and we're going to have excited state. And for the field, we're going to have 0 photons and 1 photon for the problem that we would like to study. So we assume that we have a function or a ket psi t, which is the state of the system after some time t, and we consider that we're going to have ekt, which is a probability amplitude associated with it being excited, and it is excited with 0 photons plus 1 minus exponential minus 2 kt, which is the probability amplitude that it has decayed. And then you have ground state and 1 photon in the field. So you can clearly see that we're doing something a bit phenomenological that takes into consideration that the whole system, field plus atom, can be in the excited state with 0 photons and in the ground state with 1 photon. And this, if you want, this is the vacuum state. Now, this is not a product state, can you see? Because you cannot factorize this. So this is no product state, which means that this is entangled. How are we going to extract then the influence of the field from that? We are interested in finding a state description for the atom alone. So let's have a look. In other words, we are interested in the reduced state in which everything or every information associated with the field can be traced out, right? We cannot factorize things. We have at the beginning an entangled state, which you can see from here, which is associated with the system. So the first step that we have to do to find the reduced state is we have to find the density matrix for the whole system. So let's have a look. We're going then to compute psi t. Psi t. This is our density operator, right? So in other words, we just have to write E minus kt E0 plus square root of 1 minus h minus 2 kt G1, and as a function of the bra, we're gonna have E0 E minus kt plus 1 minus e minus 2 kt square root G1, correct? So this is what we're going to compute and we're going to expand on this. So this means, this is our whole. This means that whole is going to be, let's do all these operations, and you have some distributive operations here that we need to take care of. E minus 2kt, E 0, E 0 plus 1 minus E 1 minus E minus 2 kt, G1, G1. So these are our diagonal parts. If you calculate the trace, pretty much all the rest is going to disappear. This is like coupling the same states. And then here you have E minus kt, 1 minus E minus 2 kt, E 0, G1 plus E minus kt, 1 minus E minus 2 kt square root, G1, E 0. Okay, so we wrote the density operator. What we need to do now is we need to trace out the degrees of freedom associated with light. So let's do that. According to the prescription that we had to sum up over these degrees of freedom. So we keep those related to the atom, which is the excited and the bound state. And here we have sandwiched these 0, whole 0, m plus mu, no, sorry, let's exchange the index, 1, whole 1, mu, and then here we have this operator, mu, and me. Okay, so what we need to do is we're getting rid of the degrees of freedom that we associate with light. So first was compute the density matrix, then you get rid of the degrees of freedom that you associate with light. So you trace them out, and when you compute this, what remains are those degrees of freedom associated with the atom. So what you can see here, okay, this goes here, doesn't, so that you don't confuse it, is because it's too long. So this is the continuation of this guy. Okay, so we need to compute 0, whole 0, and 1, whole 1, whereby 0, whole 0, and whereby these are expressions associated with the degrees of freedom getting rid of. So this gives you E minus 2kt, E. Do check this but what you can see is that we have no 0 here anymore. We sandwiched it, so we got rid of it. And when you calculate 1 whole 1, you have 1 minus E minus 2 kt GG. Again, you got rid of all the ones. Now we need to calculate these other guys, this and this. This we have done, right? So let me emphasize it. Let me make it like this. And let me make it like this. So I'm going to calculate this. Which is just inserting then this expression here, right? So we get nu e mu, whereby this, because these are orthogonal states, in fact orthonormal, we have two Kronecker deltas here. So we're gonna kill everything in the sum apart what is related to the excited states. So if you look, you have sum over these two indices and you have these things. So in the first case, we just have something related to the excited state. So we kill two sums. And in the other case, where we have nu 1, 1, you're going to find that you have, substituting again, 1 minus E minus 2 kt nu G mi, and this is again delta nu G delta mu G. Therefore, I can say that the whole of the atom, putting all this together, is minus 2 kt E plus 1 minus E minus 2 kt G. So let's have a look at this result. One thing that we can really see is that this behaves as expected. So at the times, first thing, apart from behaving as expected, we have a situation that degrees of freedom associated with field are gone. Which we wanted, right? And this behaves as expected because at a time t, there is a probability E minus 2 kt that the system is in the excited state. These probabilities we put a bit by hand because we put the amplitudes by hand as well. But this is what you expect. You expect that at some time, you remember what the density matrix is. These are probabilities multiplied by projectors. So you have here the excited state, and at that time t, there's a probability that the system is in the excited state, and this is e minus 2kt. So it decays exponentially with time. The longer you remain in the state, or the longer t is, the less likely it will be that it is there. And correspondingly, this is probability that this is going to go to the ground state. And this is interesting because you can see that the state of the atom is mixed, right? If you look at the state of the system is just, if you consider atom plus light, is psi t, right? So we can see that, and this is important, the state of the system this is psi t, and this is pure, right? And in fact, if you look, when we started to calculate the density matrix, where is the density matrix? Here. You can see because we took psi t. So in whole was this, just a single projector. But the state of the atom is mixed. Because what you're going to have is we are going to have the entanglement. So if you look, whole atom is not described by a single projector. And this is because we have entanglement. And this is because we have entanglement atom plus field. The entangle is the atom is entangled with the field. So this does make big difference. Now, just to close, I'm going to do this after this example because it's very short. We are going to see how the density operators evolve. So how is the unitary evolution of density operators? So let's consider psi t, and this is going to evolve from 0, just for simplicity, but you can consider any initial t0. So if, and this is, if you remember, time evolution operator. If for some reason at time t equals 0, rho 0 is j, pj, psi j, psi j. So usual formulation, density matrix has to do with projectors. Then we can also say that rho t, so if you evolve it, you're going to have sum over j, pj, psi t, psi t, where I can say, for instance, this is phi j, psi j. So this is going to give me pj u t psi j, psi j u dagger t, meaning that this is going to be equal to ut rho 0 u dagger t. And this is rho t. Which means, and this is quite interesting, because you are not seeing any mixture that is being introduced. You are not seeing any changes in the projectors. You just have some evolution operators on the left and on the right. That's it, right? So this is important because a state which is initially pure will remain pure. So that mixed states can only arise if, and only if, there is some classical uncertainty. Say you're doing an experiment and for some reason there are uncertainties which you need to take into consideration. Or during the evolution, the system becomes entangled with other systems, which means it's no longer going to be just that closed system. It's going to be a subsystem of something bigger. And open quantum systems are going to be dealt with later in the course. And they interact or become, yeah, it's pretty much the same, entangled and or, okay, with external systems during the evolution. So this would be, for instance, one case where this would hold. So this is what we're going to discuss about entanglement. And the next topics of this module are going to be related to WKB approximation, which is quite nice if you are dealing with arbitrary smooth potentials. So thank you for watching.